Hello, we're going to be taking a look at an example here dealing with a box that's on a ramp. So in this one, we've got a 4.05 kilogram box of Dreams. It's on a ramp that's at 25 degrees. So our box, we're going to say, is going to start from a rest and it's going to slide down a ramp. It's going to go 4.5 meters in 6.50 seconds. And we want to figure out what is the acceleration of this here box. So when you look at that first question, we got a box, it's on a ramp, it's at an angle, we got a mass and stuff. But if we're talking about it's starting from a rest, it's going 4.5 meters, 6.5 seconds. What's its acceleration? We're just talking about one-dimensional motion stuff here. So what do we know? We've got our distance here. We got a time. It's starting at a rest. So our initial velocity. So we got initial velocity 0. Delta x 4.5. Time is 6.5 seconds. What's its acceleration is our question here. So if I look through my various different equation stuff or equations sheet, we'll be looking at the delta x is the VIT plus 1/2 AT squared. That's just one of our one-dimensional motion equations because it's just sliding down a straight ramp. That's one-dimensional motion. So we know the distance, 4.5 meters. We know the initial velocity is 0. We know our acceleration. No, we don't know our acceleration. That's what we want to find. And time is 6.5 seconds squared. So if we start working on algebra size in this, 1/2 times 6.50 squared, we want to figure that part out. That's going to give us, on this side here, about 21.125 times A, and that's going to equal our 4.50. So we'd be dividing by 21.125 on both sides. That would give us an acceleration of, when we work it out with our 3 sig figs based on everything else being 3 sig figs, 0.170 meters per second squared. So that would be our answer for part A. Just go back on that, make it a little bit nicer box. Ooh, that's a pretty box. We can make it three-dimensional if we want. Woo! Okay, so our acceleration is 0.1706 or 0.170 centimeters meters per second squared. Sorry about that. What is the force of friction between the box and the ramp? Now we're going to start dealing with some forces. One thing we do know, we got this acceleration here. We just solved for acceleration. So that means that our forces do not cancel out because it's accelerating. It's not going to be balanced. But we'll be using that idea that our net force equals mass times acceleration when we look at those different forces. So if I want to look at drawing a free body diagram here, I've got a box. It's on a ramp, so it's sort of angled down a little bit. As usual, we got a force of gravity, right? That's a really not very straight down arrow. It should be more straight down, but you get the idea. Ramp is going to have a normal force here, Fn, and then there's some friction going up the ramp. And we don't really have any further forces on there. There's just those three. That's typically anything that's on a ramp. Those are going to be our culprits. But what we can do, sort of like our other example we're looking at, we're going to break this force of gravity up into some components so that it's on the same scale as our other ones. Our angle is 25 degrees from the problem. So I'm putting that 25 degrees there. That's where that's always going to show up if we're dealing with a box on a ramp, anything that's on a ramp. We can go through geometrically and prove why that would be that angle there. I'm not going to do that at this point, though. So it's sort of like we did last time. I got this force of gravity. It's going to equal mg, mass times gravity. If I look back up at the problem, our mass was 4.05 kilograms. G is 9.81. So if I multiply those two together, I'd get a weight of 39.7 newtons. And I want to figure out what these two components are. Those are going to be doing our trig stuff again. This is our adjacent side. So if I do a cosine of 25 degrees, that's going to equal that adjacent side here. I can call it x over 39.7. And if I multiply those two together, 39.7 times the cosine of 25 degrees, that would be giving us just over 36, so basically 36.0 newtons. 36.0, that's a 6.0 newtons. And if I do the same thing with the other side here, that would be our sine. So sine of 25 degrees, the opposite side, is going to equal y or x or whatever you want to call it, Billy Bob Joe, over 39.7. If I multiply those two together, 39.7 times the sine of 25, that'll give us this opposite side here, and that would end up being 16.8 newtons. All right, so I've got those sides there. And I want to figure out the coefficient of friction here. Or not the coefficient of friction, I just want to figure out the force of friction for the moment. So if I scoot down a little bit, if I've got these forces don't balance up, I know that the box is accelerating down the ramp, accelerating down this way. So it means that 16.8 newtons and the force of friction are not equal to each other. If they were equal to each other, we'd be going at a constant speed, but we just found an acceleration. So one of Newton's second law says that our net force is going to be equal to mass times acceleration. So if I look at net force, you can get that by doing mass times acceleration. You can get that by combining our forces. So if I look at these two, 16.8 minus the force of friction because they're in opposite directions, that's going to equal our mass times acceleration. The mass we said is 4.05 kilograms from the original problem. The acceleration we found out in the first part of our question is 1.70. That's a 16.8 again, not the prettiest. So if I work that out, multiply 4.05 times 1.7, that's going to be about 6885. And if I got 16.8 minus the force of friction, if we work that out, subtracting the 16.8 over to this side, I'd have the negative force of friction when we do 0.6885 minus 16.8. That would give us negative 16.1115. So our force of friction, if we just make those positive then and do our 3 sig figs, 16.1 newtons. And that's one of our answers we're looking for. Okay, moving right along. What is the coefficient of kinetic friction between the box and the ramp? Well, we got friction here. The force of friction, as you might recall, hopefully recall, the force of friction is mu times the normal force. If I look back in my picture, the normal force right here, I haven't figured that out yet. But I know the box is moving this way. It is not moving up or down. It's not falling through the ramp. So that normal force and this 36 newtons do cancel out. They'll be equal and opposite. So my normal force is 36 newtons. I'm going to use that in a second. So remember that part for a moment here. Our force of friction, like we were saying, is mu times the normal force. I was just saying that our normal force is 36 newtons. And our force of friction we just found out is 16.1. So I'm going to plug 16.1 in here. And if we divide by 36, mu k, because it's sliding, it's moving, would end up being 0.447 when we do that with our 3 sig figs. Okay, last question. We're almost done. What is the final velocity of the box at the end of the 4.50 meters? So when we look at that, we're looking at final velocity, VF. We've got that distance. This is basically a continuation of what we were doing way back here in part one. That's just a one-dimensional motion stuff. We know the acceleration, we know the time, we know the distance. So we're just doing another one-dimensional motion problem to figure out that distance or that final velocity. So it really has nothing to do with the part B and part C in here, the forces part. So if we want to figure out our final velocity, a one-dimensional motion thing, probably the easiest one, final velocity would be the initial velocity plus AT. Since we know our initial velocity was 0, if we look back, the acceleration we found was 0.170, and the time from back in the original question was 6.50. So if I figure that out, that's going to give me 1.11 meters per second. Well, bam! So that is the end of this particular example. Working out here just as our running out of time on our free recording here. So, remember, if the forces do not cancel out, if it's accelerating, you're using that net force equals mass times acceleration. That's always going to be a part of that.